Good morning. Welcome. It may not be morning where you're watching, but that's okay. So today we're going to do the second day's worth of content videos to prepare for our third class. And last time we covered the first two sections of our prerequisites chapter. And this time we're going to cover three more sections. We're not going to include the last section of our P chapter, and I decided that this time we would go ahead and label our different sections, especially since we had three, but maybe we'll just keep on doing that so that we can keep things sorted because, as you know, your homework will be sectioned out by different sections as well. So we'll just keep going with the labeling. So polynomials and factoring is what we're going to talk about in this first of three sections. So this is going to be a long video, but feel free to pause and take breaks as you want to. And so this is an intimidating definition, but what we can do is we can just say, hey, all of these A's with subscripts. So this is like A sub 0 and this is A sub 1 right here. And you would just keep going to however many you need. And that's what it's saying. All of these are just numbers. When you see a real example of a polynomial, you'll just see numbers here and you won't see all these letters and subscripts. The x's will be x's though, and but when you get up here, it will be a real number, an integer. It will a whole number actually, a counting number. Um, and so you won't see these n's and n minus ones in your real example. This is kind of just it. It's complicated because it's trying to be generic and represent every possible polynomial that you'll ever see. And what it's saying is that you'll have some numbers attached to the letters, except one number will be standalone, but all of the others will be attached to letters. And you'll have the letters of a single power. Um, and we'll just look at some examples and that'll probably clear it all up. When we're in standard form, that means that we have descending powers, so the highest powers are first, and then you go down all the way. This is understood to be like x to the 0th power. This is x to the first power. You would have x to the second and x to the third, and then your highest power. And we would say this is an nth degree polynomial because the highest power is n. And then if you have monomials, mono means one, and so that would be just like a sub 0. That would be a monomial. Or you could have 3x squared. That could be a monomial, but it would just have a single term. So that's what monomial means. A binomial, bi means two and tri means three. So a binomial would have two terms and a trinomial would have three terms, but we usually use polynomial to represent the arbitrary. Um, we don't know how many terms it has. It has many terms, but it really, even one, even though one's not many, we call a polynomial. And then here are real examples of polynomials. So these are all examples. And then we can rewrite them in their standard form, which, remember, that means that the highest power goes first, and then it goes in descending order. And so the highest power going first, and then going in descending order. Now, when we put it in standard form, it's easier to tell the degree of the polynomial because the degree is going to be the superscript, the power of the variable that is the first variable that you have. So 7 and 2. Now, this one doesn't even have a variable, but we can write it as x to the 0th power because x to the 0th power would just be 1, and 8 times 1 is just 8. And so we would have the degree there. Notice that the leading coefficient is the number that's attached to the term with the highest power. So that's what degrees are, and that's what leading coefficients are. And then the degree of complicated polynomials that have multiple variables, more than one variable, you would add the powers of the variables together. So 3 plus 6 is 9, and then 1 plus 1 is 2, and then 7 plus 4 is 11. And this is actually the highest power. And so the power of this polynomial would be an 11th degree polynomial because the highest power is 11. And then the following expressions are not polynomials. So anytime you have a radical that you can't get rid of and simplify out, um, that would mean you would have a power that was not a whole number, not an integer. Or if you have a negative power that you can't get rid of and cancel out, so it really needs to be a whole number, a non-negative integer. So, and then we can add and subtract polynomials. So here, let's go ahead and do some addition and subtraction. For the x to the third, we have a 5 and an understood to be 1, so that would be 6x to the third. So basically, we're combining like terms on here. And then for x squared, we would have the negative 7 and the positive 2, so that's going to give us negative 5x squared. And then for the x, we would just have the minus x because it's the only term like that. And then for the constant, we would have negative 3 plus 8. And so that's going to give us plus 5. So that's how we would combine these like terms. And then here we would have 7, and we would distribute this negative, so this would be negative, this would be positive, and then this would be negative, is how we would just, and that's how I would think of a negative, is I would first distribute it to everything, and then just that way you won't forget. So the 7 and the negative 3 become 4 x to the fourth, and then the minus x squared and the now positive 4x squared become 3x squared. We didn't have an x to the third. And then the negative 4x, and now the negative 3x becomes negative 7x, and then we have the plus 2. And that's combining all of this term for us. We want to find the products of these two binomials, and whenever we find the product of two binomials, we almost always want to use FOIL. And so I believe we mentioned FOIL last time. What we want to do for FOIL is we want to do first, outside, inside, last. And I usually do it in that order, but you don't have to do it in that order. So if you accidentally flip the inside and the outside, or that's fine as long as you do all four. And so first would be the two first terms. So the 3x times the 5x would give me 15x squared. Maybe I should write that lower actually. And then the outside would be the 3x and the 7, so 21x. And then the inside would be the negative 2 and the 5x, so negative 10x. And then the last would be the negative 2 and the positive 7 for negative 14. And then you can always combine the outside and the inside together, or Yeah, you should always be able to combine them together because they should have, um, or at least if they're the normal type of binomials that we're used to, you should be able to combine them together. That should give us 11x. So 15x squared plus 11x minus 14. Here, a lot of these will be on your formula card uh, in this form, not in they won't have the examples, but they will have um, these in a little list for you. And they may not look exactly like in this order, but it will give you all of the same special products that you can do. And so what we do with those is we say, oh, okay, if we know that we have, basically these are conjugates because the only difference between these two is the sign. And so whenever we have a conjugate, when we FOIL, the middle term falls out because we would have positive UV on one and negative UV on the other. And so the positive UV and the negative UV cancel out. So you're left with the U squared minus the V squared. So the product of the first terms and the product of the last terms, since the O and the I, the middle terms, cancel each other out. And then if you were to have um, squared, both of them would be positive in that case instead of one positive and one negative. So you don't cancel it out. And so the two middle terms add together and they're both positive. So you get twice the outside or twice the inside because they're going to be the same thing. And then if you have negative, both of them are going to be negative, and so you would get that. And then it turns out if you FOIL this and then multiply it again by u plus v, because you've got three of the u plus v's there, then you will get this long term. And so that'll kind of let you know that, hey, I don't have to do all of the um, algebra. I can just use this format. Um, and I can, whatever my U is, and your U is probably going to be more complicated than just one letter. So it might be like 3x or um, something like that, 3xy or something like that. Um, but you know that you can have all of these to use uh, if we want to do some things. So here we're wanting to multiply all of this out. Then sometimes it helps us if we can express it as if it were. So this is a trinomial times a trinomial, but it helps us if we can express it as if this were like one term. So this is kind of looks like a binomial now, and looks like a binomial. And what's more is this is exactly the same thing as this. And this is exactly the same thing as this. And we have different signs. So now we know we have conjugates. So by grouping these terms together, if you can find a grouping that helps simplify it, then absolutely do. If you can find a grouping that makes it look like any of these, then absolutely do that. So that's what we want to do, is kind of try to manipulate the problems that we're given so that they look like what's on our sheet if we can. And then, so this is the negative and the positive. That's the very first thing that we see on the sheet. And so we know we have the u squared and the v squared, and it's the difference between those two. And so this is our u, x plus y, and 2 is our v. And so we have u squared minus v squared. And then we FOIL out the u, and then we just square the v because 2 squared is just 4. And that's our final answer for that one. And so that's one application. Here we can factor this one. And we'll use a kind of grouping technique on this one as well. And so uh, basically, I want to look at this part, and then I want to look at this part. And so what I'll say is, okay, on the first part, I could factor out an x squared. And so if I factor out an x squared, I will have x minus 1. And then if I look at this, I should say, oh, this, I might be able to get an x minus 1 out of this as well, especially if I take out a negative 4. And so if I take out a negative 4, then that will leave me with x minus 1, because the negative and the negative on the negative 1 and the negative 4 will combine to give me positive 4, and of course the negative 4 times the x will give me the negative 4x. So I have what I want there, and now I can basically treat this as if it's a variable on its own. So I've got this, and I can say, okay, this is x squared minus 4, and then this is x minus 1. But if I'm factoring, I'm not really done here, because I know that my x squared minus 4 can keep going. It would be that very first u squared minus v squared, right? And so I know that I can do u minus v and u plus v to factor it. And so this is my final answer on this one. And so when I'm factoring over the real numbers, I can even factor something that looks like this, where 3 is not a perfect square, but if I'm if I if I'm not confined to just integers, if it is over the real numbers and not just integers, then the square root of 3 is real. And so I can do plus or minus the square root of 3, as you see here. This is really just like what we talked about before. This would not be completely factored, because we know that we can keep going. Oops, sorry about that. We know that we can keep going with the x minus 4. So the x minus 4, it needs to factor into x plus 2 and x minus 2. So that would need to keep going, and then we would have x minus 1. So this would be the complete factorization, and this is not completely factored. But if we have not the difference but the plus between them, then we look back at our special factors and there's not one. There's not a way to factor if there is addition between the two squared values. So this one is considered to be completely factored. Okay, so we want to factor each expression by removing common factors on these. And so this one is even and this one is even. So we know we can pull out a 2. We also know we can pull out an x. So 2x, that'll leave us with 3x squared minus 2, right? And so that looks right, because if we multiply it back out, we will get the 6x squared the 6x cubed that we had, and then the minus 4x. And then for this one, we know that we have 4 divides into everything, and let's go ahead and pull out negative 4 so that we don't, and then let's do this in a couple of steps. So we'll probably be able to do more x squared plus 3x, x squared minus 3x, right? and then plus 4. And now we hope we can factor, and this is kind of a reverse FOIL, and we haven't talked about it yet. Actually, let's save this because it's only told us to remove common factors. So we will save this, but realize that this is not the final answer because we can still keep going on this one. But we will leave it as our final answer since it only asks us to remove common factors on this one. And then on part C, we have 3 and then x squared that can be pulled out of all of them, and that'll leave us with x squared plus 3x plus 2, right? And just kind of double check that. And so that's our answer there. And then, we've got x minus 2 and x minus 2 on this one. And so when we pull that out of both, we'll do x minus 2. We'll have 2x plus 3. And that will be our common factor that we've pulled out of both. And then this is a little bit reverse of what we saw before. Not always, but if we want to go the other direction and we want to, we have this answer and we want to factor it out, then we can do that this way. Also, this is a little bit of what we saw before. If we have twice times UV, whether it's positive or negative, we know that we're going to have something that's a perfect square. And then we can even get the difference between two cubes will factor easily, or the sum of two cubes even will factor pretty easily into this nice format. So we can use this as a reference to factor in the future. And so notice here, when we have the difference, we go back to our formula and we know that we have that is exactly how we can get it. So it's opposite signs whenever we do have a difference there. And so what we want to do here is use that principle, this principle, and factor on these. So on this one, I would have my x plus 2 minus y and my x plus 2 plus y. And notice how I have a plus on one and a minus on the other. And I kind of flip-flop the order, but it either way is fine. And so now we can say this is the same thing as x plus 2 minus y, and then x plus 2 plus y. And we would do the same thing here. 16x to the fourth is the same thing as 4x squared, quantity squared, and then 9 squared. And so we could factor this as 4x squared minus 9, and then 4x squared plus 9. Now, on the 4x squared minus 9, we can recognize that that is 2x squared. So 2x squared minus 3 squared. And so we can further factor it into 2x minus 3 and 2x plus 3. But the 4x squared plus 9 would need to stay. And so that would be our final answer on this one. And so a perfect square of a trinomial, if you had a perfect square, then it would look like this if you had positive signs. But if you had a negative sign, then you're going to have the negative. And so the middle sign is going to match the sign in your perfect square. So if it's negative here, it's always going to be negative here. If it's positive here, it's always going to be positive here. And so here we have a couple of examples. And hopefully you can see that this is x and then of course quantity squared, and this is 5 squared. But if you take the 5 and you double it, then you've got your 10. So hopefully you can recognize that this is the format of one of those special ones. And we have the negative here, and so it is a perfect square with x and 5 with the difference. We have the same thing here. We can write this as 4x. We can write this as 3. And then if we do 4x times 3, we have 12x, and that's twice of 12x is the 24x. So we recognize that we can have this also as a perfect square. Because it's positive, we have the plus sign here. And so we have the 4x plus 3. And when we FOIL all of that out, we will get our original. And even with cubes, we can do this. So we have the sum of two cubes and we have the difference of two cubes. When we have the sum of two cubes, the negative is here in the trinomial. When we have the difference of two cubes, the negative is in the binomial. So we will always have a binomial and a trinomial. We will always have exactly one negative, but the negative is going to be in the trinomial if you have positive between the two cubes, and the negative is going to be in the binomial, the two-termed one, if not. So looking at an example, we have the difference between two cubes here. And because we have difference, we know that the binomial is the one that's going to have the negative sign. So we have the x minus 3, and then we have the u squared plus uv plus v squared. So the u squared, the v squared, and then this is just u times v. And again, it's exactly the same values here and here, the difference being these signs. And so that's the difference between two cubes. And again, that's going back all the way up here and using this formula that will be on your formula card to write that out. So keep that handy. Oh, okay. We talked about this earlier, and I almost did it earlier, and then I was like, no, wait, we've got this later on. So, whenever you have a trinomial, three terms, you can factor it into the product of two binomials. We call this quadratic, in other words, because you've got the x squared. So, this is the factoring of a quadratic, and uh, we always want to say, okay, how can we break down A? What products will multiply together? What factors will multiply together to give us A? And what factors will multiply together to give us C? And we just try different combinations of those until we get the middle term, the O plus the I, to add together to give us B. So this is kind of an art. What I usually do is I make a guess for A and I make a guess for B. And then based on that, I'll say, okay, what combinations of C, what products um, do we have for C? And then what combinations of those with the A's that I already have will give me what I need to get that middle term of B. So now that we've talked about how to do the binomial factors, the quadratic, factoring a quadratic, let's actually work an example for this one. So we want to factor on this one, and we have the 2 and we have the 15. And 2, you can really only do that like 2 times 1, but the 15, we could do that as 15 times 1 or 3 times 5. Usually, the factors that are the smallest factors are the ones that you want. So, especially when you have a small b, when your b is small. And so, we will always kind of have our spaces, and we'll have something times x and something times x, or maybe just x. And then we'll have plus or minus, and then the number here. So we're kind of filling in the blanks. I know that I want to try 2 times 1 because really this is a prime number, and so 2 times 1 must work. And then we need some combination of the 3 and the 5, most likely. And we want our middle term to be positive 1. Well, if we do 3 here and 5 here, and especially if we do this one as the positive one and this one as the negative one, then we know that our 2 times 3 is going to give us positive 6, and our negative 5 times 1 will give us negative 5. So positive 6x minus 5x will give us our 1x that we're looking for. Now, I could have tried the flip-flop of these to begin with, and experience taught me to kind of think about it in my head first before writing the numbers here. So thinking about the 2 times 3 and that giving me 6, and the other one being 5, I was like, oh, yes, that difference is 1. And so that works. So that's how my thought process kind of goes on those. Factoring by grouping. So if they tell you it's factoring by grouping, that helps because you've you've got to think, okay, I'm going to group these together somehow, probably in the order that they're listed, but I may need to rearrange them in order to group them. So be aware that that kind of is going to happen. And what we're going to try to manipulate is to get some common factor. So right now I can see that if I am factoring this together, then I can pull out like x squared, but that leaves me with x minus 2, and that x minus 2 is a factor of this. So if I pull out a negative 3, and I can do x minus 2 here as well, and then the negative 3x gives me back this, and then the negative 3 and the negative 2 gives me back the positive 6. So um, that's a lot of writing there at the end, but I've got a x minus 2 and an x minus 2, and that's exactly what we want when we group. We want one of the factors from our first group to match the factors from our second group, and so that way we can take the x squared and subtract the 3 and then have that x minus 2. And we can go further if this is over the real numbers and say that this is x plus the square root of 3 times x minus the square root of 3 and then x minus 2, because we know that we have the u squared minus the v squared here. And so that's our factoring by grouping. Now, when our basic properties for factoring all polynomials, not just factoring by grouping, is the first thing we're going to want to try is the easiest, and that's to factor out any common factors using our distributive property. So if you notice common factors, you're going to want to try that. Our second step is to look at our formula card and look at the special polynomial forms to see if any of those match. So that's step 2 when you're factoring. Our third step is to do the kind of quadratic factoring that we were just talking about, where you don't know what this is, and you don't know what this is, and you don't know what this is, and you don't know what this is, but you take all of the factors of A to make your first product, and all of the factors of C in some combination there is going to make your second product. But you know that the combinations of both have to give you a middle term that's going to give you B. So that's kind of the trial and error. Hopefully, though, especially if you've already factored out common factors, the A, B, and C won't have a lot of factors. They won't be very big numbers, and so that'll be helpful if that's the case. And then our last effort is what we just tried on the factoring by grouping. So that's the fourth thing that you can try on your factoring. And that is our polynomial section. Our next section uses polynomials, though, because it's rational expressions. And so for rational expressions, the first thing we're going to talk about is the domain. And so you've got the set of real numbers, and if you have just a normal polynomial, you're going to have like the whole set of real numbers is your domain. But if you have the rational expression, then you're going to have basically a polynomial over a polynomial. And what we're saying when we have that is there's certain things that we're not allowed to do. So we're not allowed to, number one, divide by 0, and number 2, we're not allowed to take an even root of a negative value. And so we'll look at examples of that as we go. But these are the two things that we want to be on the watch out for. And so we just want to make sure that all of the numbers that we say are allowed in the domain are so that we never divide by 0, and that we're never taking the square root or the fourth root. That's what I mean by an even root. Square root, fourth root, sixth root, eighth root. We don't usually get that high. We usually like to do the square root or the third root, cube root, but we don't usually go higher than that. But the square root would certainly qualify as an even root, and we don't want anything under the square root or under any even root to be negative. And so here are 3 examples. And the first one's just a polynomial, so there's no way that we could do anything inappropriate there. There's no way we could divide by 0 because we're not dividing by anything. And there's no way we could take the even root of a negative value because we don't have the root of anything. So for this first one, we would say the domain is all reals. And sometimes I can abbreviate that by just writing the R with like an extra line in it, and that means all real values. And for B, though, we do have to worry about number 2, right? Because it's a square root. And so we just need to make sure that x minus 2 is positive or 0. So in other words, x minus 2 has to be greater than or equal to 0, because the square root of 0 is 0, and that's fine. That means that x has to be greater than or equal to 2. And so we could say all reals where x is greater than or equal to 2. And then for this last one, we don't want to divide by 0. So we don't have the problem with number 2 on the last one. We don't have to worry about it. But we do have to worry about dividing by 0. So here we would say all reals except 3. So x cannot equal 3. Might be another way of saying that. So as long as x does not equal 3, everything's good. And so that's the domain. Here, the quotient that we've been talking about on several of these, a quotient is one number divided by another. And so a quotient of algebraic expressions is called a fractional expression because it's a fraction, and it's a fraction of expressions. And if it's one polynomial over another, so if it happens to be a fractional expression that's a polynomial divided by a polynomial, that's what we define to be the rational expression. So the polynomial divided by a polynomial is our rational expression. And these are all fitting into that category of rational expressions. So here we want to simplify lots of times when we're doing the rational expression. So here we have a polynomial divided by a polynomial, but we can factor out a 3 from this, and we can factor this in quadratic factoring, and it turns out both of them have a common factor of x minus 2, so we can cancel the x minus 2, and this is extraordinarily common stuff whenever we deal with rational expressions. We want to simplify our answer after we've done some stuff, and when we simplify, we end up canceling factors out. When we cancel stuff out, we need to say, hey, remember that x cannot be equal to 2. Now, if we had not canceled this out, we wouldn't have said this part. But whenever we simplify, unless it asks us for the domain, but if it doesn't ask us for the domain, we don't have to tell this stuff unless we've canceled stuff out. And so this and this are the same as long as x does not equal 2. And anytime you've canceled stuff out, you have to tell only the stuff that you've canceled what it cannot be. You don't have, if it had been left in there, you wouldn't have to tell it because it would be obvious, because it would be part of the denominator, the answer. But when you've canceled it out, you do have to tell it. So I hope that makes sense. Okay, so this is saying what I just said right here. So here, even though we know that x can also not be negative 5, we haven't listed that because we haven't canceled that part out. So we've only listed here the stuff that we got canceled out. So basically what we've done here is we've factored both of these, we've factored both of these, and then we've canceled stuff out. So we When we factor this first one, we have the 2x minus 3. When we factor down here, though, that's also going to leave us with the 2x minus 3, so those get canceled. And when we set 2x minus 3 equal to 0, we end up solving it, and x is 3 halves. And so we know x can never be 3 halves because that makes the denominator 0. And then also, when we factor this denominator and this numerator, we get x minus 1 as factors. So we know those cancel out. And when we factor this stuff and this stuff, we get an x factor. And those cancel out. So x, setting it equal to 0, it can never be 0 because we canceled it out. Also, we canceled out the x minus 1. And x minus 1 used to be in the denominator, and so it was canceled out. And so everything that was used to be in the denominator, be sure to write that. It can't be those. We leave off the x minus, or the x equal to negative 5, even though we know that's not part of the domain because we didn't cancel it out. So that's just an FYI. When it asks you for all of this stuff, it's asking only for the stuff that you actually canceled out and not for the stuff that we know is not in the domain, unless it explicitly says what is the domain, and then we would say it's all reals except not negative 5, not 0, not 1, not 3 halves. So if it explicitly asks for the domain, you include it, but if it's only asking you to simplify, then you give the simplified expression and the stuff that you canceled out. Hopefully that's clear. Let me know if you have questions on that, and we can talk more about that. Okay, so common denominators. So in order to be able to combine this stuff, we need a common denominator. Just like if we were adding 3/4 plus 1/2, we would need it to both be over 4 so that we could combine. And that's the same thing is true when we have algebra. We need these denominators to be the same. And we can do some manipulation to make them the same. So when we get the common denominator, our common denominator will be x times x squared minus 1, but x squared minus 1 is x plus 1 times x minus 1. And that'll help me here because I'll know that this first term I need to multiply by x times x plus 1. So x times x plus 1. Really, I need the bottom to be that way, but what I do to the bottom, I have to do to the top. And then for the second one, I really need to multiply it by both these things. And I'm just going to call this x squared minus 1 to save some space because, both of the product of these two is going to be x squared minus 1. So I multiply the top by x squared minus 1, put parentheses around it, and what I do to the top, I also do to the bottom. So that's also x squared minus 1. And then for the last term, I really just need the x on it to make it x times x squared minus 1. So I multiply, I'll put parentheses around the numerator and the denominator. So it's x over x. So once I do all of that, I will get 3x times x plus 1 for my first term, and then minus 2 times x squared minus 1, and then plus x times x plus 3. And this is all divided by my x times my x squared minus 1. And then I would distribute all of that and combine like terms. And so 3x squared plus 3 minus 2x squared plus 2 plus x squared plus 3x, right? Okay, and then the denominator, I'm just going to leave the denominator like that. And then we want to combine like terms. So my 3x squared, negative 2x squared, and then positive x squared. That will leave me with 2x squared. And then my plus 3x is all by itself, right? And then my plus 3 and my plus 2 becomes plus 5. And then we have x. I'm going to go ahead and distribute these just in case to remember that we may be able to cancel them. And then let's FOIL this out and see if we can cancel anything. We may not be able to, but that's okay. And I know it's going to be 5 and 1 because that's a prime. And I know it all has to be positive. Ooh, so yeah, there's really just no way we can get 3 in the center. Even if I put 5 here, that would still give me a lot more than 3. And certainly if I flip-flop them, that would give me more than 3. So I can't think of any way to factor and have whole numbers, and certainly that we would need whole numbers to be able to cancel anything. So I'm going to go ahead and say that that is the simplest form right here, and so leave that as our answer. And it is a polynomial divided by a polynomial. And we did not cancel anything. So we don't need to worry about saying x cannot equal blah, 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 because if we were asked what the domain was, we would have to say x cannot be 0, x cannot be positive 1, and x cannot be negative 1. But since we didn't cancel any of those, we don't say any of that. We just say this is our combined expression. And then here's another example. This one's kind of already worked out for us, but it involves us doing a little work and in addition to finding the common denominator. So here we want to find the common denominator in the top part, and we want to find the common denominator in the bottom part. And then we will flip and multiply. And we may be able to cancel some stuff out here. We'll see. So for 3, we want a denominator of x, and so we multiply by x over x, and that's what we've done here, and that's where this minus 3x comes from in the denominator of x. And then for the bottom part, we need the denominator to be x minus 1. So what we've done is we've taken x minus 1 divided by x minus 1 and multiplied that by the 1. And so that's why we got the 1 times x minus 1 in the top part so that we could have the x minus 1 in the bottom part. And then it just, we're left with the minus 1 for right here as well. And then we just kind of, say that's 3x, and this is x minus 1, and then minus another 1. And so that gives me, x minus 2 in the denominator for right here when I combine everything. And this is just 2 minus 3x. But the important part is once I have it as two fractions, a whole fraction over a whole fraction, I can then flip the bottom fraction and multiply. So flip and multiply. And that's what I've done here is the x minus 1 now is the top and the x minus 2 is the bottom, and I'm multiplying. And there's nothing I can cancel here, so it doesn't look like I get to cancel anything here as well. Even if I tried, I couldn't factor this to cancel with this. So nothing's going to factor. I did move the x minus 1. So it's reminded me that x minus 1 used to be in the denominator. So since I moved the x minus 1 when I flipped and multiplied, I do stipulate that x cannot be equal to 1. But that's the only caveat. And then I can just leave this. I don't even have to multiply it out. I just leave it as is and stipulate that, remember, x minus 1 used to be in the denominator, so it cannot be 1. And here's another example. This one's more complicated. Let's break it down a little bit. So the first thing that we want to do in this is we want to try to get rid of, especially this negative 1/2. That we don't want that. And so what I've done, or what they've done rather, is multiply by the same factor to the positive 1/2. Because if I have negative 1/2 and the same factor the positive 1/2, I add the exponents together, and that'll give me the 0th exponent, which means they really are canceling each other out. And if I have x to the one, or this term to the 1/2 power, with this term to the 1/2 power, when I add those two together, I get 1 whole. So I've rationalized my numerator. Oddly enough, it's going to end up with an irrational denominator, and they're going to leave that alone. I found that odd, but that's okay. We weren't asked to rationalize the denominator, so I guess that's fine. But yeah, so we distribute this, and when we distribute this, again, this becomes to the 1 whole, and this becomes to the 0th power, which essentially means it falls out, and becomes 1, and so it leaves us with the x squared there. And then we have to the 3/2 in the denominator, because this is understood to be 1 right here, or 2 divided by 2 is 1. And when we add the exponents in the denominator, we'll get 3/2 in the denominator. And then because this is to the first power, we could just remove the parentheses because that's just 4 minus x squared. And then this becomes 1, and x squared times 1 just gives me x squared. And my negative x squared and my positive x squared add together to give me 0. So I'm just left with 4 in the numerator. And this is what they leave as the final answer there. So 4 divided by 4 minus x squared to the 3/2 power, which means we do have an irrational denominator. But that's the way they've left it. If we wanted to rationalize the denominator, then we would multiply by this value or the 1/2 value, either one. Yeah, I would probably multiply by the 1/2 value one more time to rationalize the denominator, which would make you have an irrational numerator, but that's okay. So And then our last section, woohoo! So moving on to the last section, we have P5, the Cartesian plane. So let's talk about the Cartesian plane. So you've probably seen this a lot already, but as a refresher, because that's what this whole chapter is a refresher. We want to talk about the plane. We've got the x is always in the horizontal direction, and so you can think of the sun rising over the horizon. So that's x. And then the y-axis is always up and down like a skyscraper. That's your y-axis. And they intersect at the origin, 0, 0. And we do 1, 2, 3, 4. So it kind of goes counterclockwise. Um, and it starts kind of where you would think it would start, but it does go backwards when you talk about the different quadrants. So 1, 2, 3, 4. And uh, let's, so when we have a point x, y, we go x to the right, because right is positive, because as we increase on the number line, we go and move from left to right. We also write, like when we're making notes, we write from left to right. And so moving to the right, that's positive. So positive x moves along the horizon to the right. And then positive y moves up. So the up direction is positive for y. And so this is positive x and positive y, moving to the right x amount and up a y amount. Let's look at actual numbers though, because it'll all make so much more sense when we look at actual numbers. So what we're going to do is we're going to plot the 1, negative 1, 2, and then plot positive 3, positive 4. We're going to plot the origin. We're going to plot 3, 0, and we're going to plot negative 2, negative 3. So on these, the 1 comma negative 2 or negative 1 comma 2, you notice it's right here. So we go to the right, a negative 1. So this is negative 1, and then we go up 2. So that's how we got the negative 1, 2. And then our 3, 4, right here, we go to the right 3 units. You see that's 3 units here. And we went up 4 units. And then for our 0, 0, we are right here at 0, 0. And then for our 3, 0, that's right here, 3, 0. And so we go over 3 to the right, but we don't go up or down at all on the 3, 0. And then our last one is the negative 2, negative 3. And so that's right here. So we went negative direction, so left instead of right. So this is negative 2. And then negative is down instead of up. And so that's negative 3. And so that's how we got the negative 2, negative 3. So hopefully all of these make sense. And this is the Cartesian plane with our x and our y. Now let's look at an actual example. So here we have our number of employees, E, and this is actually in thousands. So this is 760,000 and 808,000 dentist offices in the United States between 2004 and 2013. T is the year, and it gives the full 4-digit year. on these. So when we plot these, and this indicates that, hey, I'm not starting at zero. I'm starting at, like, maybe this is like 2003 because this is 2004, and this is 2006 and 8 and 10 and 12. Um, and then I've also written on here that this is in thousands so that we know that this is our number of employees, but it's in thousands. And then I've just plotted all of these. So the 760 is first, and notice how 760 is 60% of the way, or hopefully 60% of the way, between our 700 and our 800. And then a little bit higher is the 774, and then a little bit higher is the 786. And then over 800, but just barely over 800, is our 2007 number. And so hopefully you can see, let me make it so you can see the numbers and the plot. Hopefully you can see how these values represent these here. And plotting it all at once, we can see that there's kind of a linear trend here going up. And we will use the distance formula, and that uses the Pythagorean theorem. So you may not remember the distance formula, but hopefully you at least remember the name Pythagorean theorem. And the Pythagorean theorem says if you have a right triangle where one corner is completely square, um, then your two legs of the triangle, your A plus B, um, the hypotenuse is always going to be the longest leg of the triangle. So if you take a squared plus b squared and add them together, that's going to give you the hypotenuse squared. The hypotenuse always being across from the right angle and always being the longest leg of the triangle. So this is always true as long as this is a 90-degree angle or a right angle right here. And then if we're measuring distance, you've always got your y distance and your x distance, but the total distance, as the crow flies, in other words, the total distance is your hypotenuse. So you've got your distance, that's the difference between the x values, and your distance, that's the difference between the y values. And remember last time we talked about distances on the number line always being positive or zero. And so we actually do the difference, but we take the absolute value of the difference, and we take the absolute value of this difference. And so this difference and this difference, if we were to apply the Pythagorean theorem, which we could because x and y are always perpendicular to each other, because x always moves from left to right, or from left to right, and y always moves from bottom to top, so moves up in a positive direction, moves right in a positive direction, and when that happens, they're always perpendicular. So we know we have a right triangle here, and so what we can do is we can say this squared plus this squared has to equal this squared, and that's exactly what we do. Our distance squared has to equal this squared plus this squared. And doing that on the next slide, we get this formula, and we can solve for distance. And so we get our distance formula just by taking the square root of both sides. Now, normally when we take the square root of both sides, what we do is we say plus or minus. But if you look at this, all of this is positive, and all of this is positive, and all of this is positive, and certainly after we square it, it's positive. So we don't even need to say plus or minus, because there's no way that the stuff under the radical could be anything but positive. So we just take the square root of both sides, and we know that this is the distance. And really, um, it no longer matters that we take the absolute value, because once we square it, it's going to be positive anyway. So we can remove the absolute values. We do have parentheses here when we remove the absolute values, but as long as we square this number, we know it's positive, and we square this number, we know it's positive, so we don't, the absolute values become redundant, in other words. And this is the formula for distance, and that's how we derived it. And it is going to be something on your formula card as well, so you don't have to worry about being able to derive the distance formula from the Pythagorean theorem. But I think it's really cool to be able to understand where these values came from, and that we just didn't make them up. So that's your distance formula, and now we can take that distance formula and we can apply it, and we can say, okay, I want to compute the distance between these two values. And I can say this is my x1, y1, and this is my x2, y2. And now my distance is going to be the square root. And I see my x2 minus x1 is squared. So I do the 3 minus the negative 2 squared. And then my symbol between them is plus, so I have plus here. And then my y2 minus y1 squared, so my 4 minus the 1 quantity squared. So 3 minus negative 2 is really just 5. So that's going to be 25 once I square it. And then 4 minus 1 is 3. 3 squared is 9. And then 25 plus 9 is going to be 34. So my distance is the square root of 34. And I could do that value on the calculator if I wanted a decimal value. Or if the homework system WebAssign will accept square roots, I could just do square root 34, because this is going to be a more precise answer than I would get if I put that in the calculator. Okay, so here we want to confirm that we actually have a right triangle. So I can find the distance between these 2 points, and find the distance between these 2 points, and then find the distance between these 2 points, and see if they fit the Pythagorean theorem. And if they do, then they are a right triangle. So what I've done is I've plotted these, and it turns out when you take these and compute the distance, you actually have to compute the distance formula on all of these, and they've already done it here for us. So we won't do it because we just did an example with one of those. So we're not going to do this 3 times over. But when you apply the distance formula, so you took the square root of x2 minus x1 squared and the square root of y2 minus y1 squared, and you do all of that, and you combine everything, you should get square root of 45. When you do that for this leg right here that looks like our hypotenuse, you get the square root of 50. When you do that for this tiny short leg, you get the square root of 5. And then when you plug it into the distance formula, oh, it actually did. So if you want to go and check all of that, you can, to make sure that they did these 3 distances correctly. This is how they computed them. And then once we look at a squared plus b squared equals c squared, well, that means that d1, which is 45, the square root of 45 squared gives us 45, and then d2, the square root of 5 squared gives us 5, should equal this d3 squared, which will be the square root of 50 squared, which is 50, and 45 plus 5 does equal 50. So it must be a right triangle because it matched the Pythagorean theorem. The midpoint formula is one of my favorite because it's a pretty easy formula. Basically, what it says is that we take the average. So if you have x1, y1, and x2, y2, then you average your x's. So you add them together and divide by 2, which is exactly what taking the average means. And you average your y's. So the middle or the midpoint is the average of the x's and the average of the y's. And so here's an example of that. I'm actually going to just steal this, steal 2 points on here. So if we wanted to find the midpoint of 3, 4, and 3, 0, then that would be something right here. So we would average the x's, so our 3 plus 3 over 2. And then we would average the y's, so 4 plus 0 divided by 2. And so 3 plus 3 is 6. 6 divided by 2 is 3. And 4 plus 0 is 4. Divided by 2 is 2. So this middle point should be the point 3, 2. And that makes sense, right? If it's going in a straight line up, this is 3, this is 3, so we would expect this to be 3. And this is halfway between the 4 and the 0 is our 2. So hopefully that makes sense. And then maybe a slightly more complicated example, we want to find the midpoint of these two. So negative 5 plus 9 over 2, and then negative 3 plus 3 over 2. Negative 5 plus 9 gives me 4 halves. 4 halves is 2. And then negative 3 plus 3 gives me 0. 0 divided by 2 is 0. So this is going to be the point 2, 0. And then the equation of a circle. And this equation of a circle is actually on your addendum to the formula card. So be sure to print out both the formula card and the addendum to the formula card that are under the syllabus section of content in D2L. So you definitely want to print both of those. Hopefully you'll bring it to the second class. I'll try to send out a reminder to do that. Or actually, I will try to print them myself and have them for you in case people do forget. And that way, if people do forget, I'll have some for you. So the distance formula helps us here and allows us to define circles. And so basically, we're taking the differences and the x's, the differences, and the y's, and that's our r, because this radius is the differences. So we can kind of construct a triangle if we wanted to think about it that way, and that would give us our differences. So that allows us to have the formula for the circle. But this formula for the circle is on your addendum to the formula card. So, for instance, if you're given a problem and let's see, let's suppose I wanted a circle that is centered at 3, 4 with a radius of 1. Well, I would use my formula, and my h would be 3, and my k would be 4, and my r would be 1. So h is 3, k is 4, and r is 1. So I do x minus h of 3 squared plus y minus k of 4 squared equals 1 squared, which is just 1 in this case. Now, if my r was 3, then I would do 3 squared, and this would actually be 9 here instead of 1, but 1 squared is just 1. And so this, I would probably omit the 1 squared and just have it equal to 1. And that would be my formula for this particular circle that is centered at 3, 4 and has a radius of 1. Now, it could be that the problem will tell you the equation, and you will tell where it is centered and what the radius is. But it could also be that they tell you where it's centered and what the radius is, and you give them the equation. So there are kind of two ways that you could do problems with this information. And then the last thing, I believe this is the last thing that we talk about, is if we shift. So here we've got these, what we've already confirmed was a triangle before, and it says we want to shift it 3 units to the right. So 3 units to the right and 2 units upward. So we're moving it 3 units in this direction and 2 units in this direction. So basically what we're doing is we're adding 3 in the x direction and we're adding 2 in the y direction. And that's what we've done here. We've added 3 to the x. And then we're adding 2 to the y. And that -1 plus 3 gives me 2. And 2 plus 2 gives me 4. My 1 plus 3 gives me 4. And this gives me -2. My 2 plus 3 gives me 5, and my 3 plus 2 gives me 5. So these are the new points of my moved triangle. So when I look at the moved triangle, I know that my -1, 2 now becomes the 2, 4. So I could label that as 2, 4. And I, in fact, see that, okay, yeah, this is 2 and 4 if I, kind of go across, right? And then my 1, -4, the one that's all the way down here at the bottom, becomes the 4, -2. So this is +4, which this is 4 right here, so that makes sense. And -2, not 1, -2. And if I were to do dots, that should make sense. And then my last point is the 0.55. And when I go down and across, hopefully that makes pretty good sense as well. I didn't draw it very well, but if you had a straight edge, you would be able to do it better. And that is a lot. um, but hopefully it will get easier as we go along. Um, so we've got a lot to cram into these prerequisite chapters. I wanted to give you a ton of examples because I know that for a lot of you it may seem like a lot. Hopefully I've given you a ton of examples to work with. We will work more examples in class for our class activities. For our class activities and for the homework, you definitely want to have your lecture notes available and your calculator available. I should have also put your formula card. You want your formula card as well. And if you can bring the textbook to class, in a laptop form, then it may be helpful to have the textbook there as well. But if not, your lecture notes with the notes added to them should serve you pretty well, especially if you also have your formula card. But you do have these as resources for the homework, especially. And so I will see you in class.